So anyways, today we're going to be talking about the search problem. We're going to be talking about some algorithms, and we're going to be focusing in on lower bounds. I thought before I get into anything too delicate, let's start talking about what the search problem is. So this is how we're going to define it. So we will be thinking about this for our discussion over an array, which I've discussed a little bit here, but as a reminder, it is just, imagine you have a collection of elements, each with an index, and I can access any one of these indices. So if I give you some number for an index, I should be able to grab what's inside as the contents of this spot in the array. So for example, if I want a sub 1, I should be able to get this number 5. So that's at position 1. It starts at 0, goes 0, 1, 2, 3. These are offsets from the origin address if you think about this from a computer standpoint. But remember, it is just a construct of the definition of just a linear collection of elements like this. But I won't go into too much about that. So presume I am given an array. Let's call it L. Given an array, and a value. Now, I'm not going to say what kind of value. It's just a value. It could be a number, it could be a word, it could be all sorts of different things. And a value x is x in L. So if I look at one of these boxes here, if I give you, say, some number for our example here, can you tell me if that number is somewhere in one of these boxes? Yes or no, true or false? If it's true, that means that it's in our array L. If it's false, it means it's not in any one of these boxes. Now, there's several different ways you can cast the search problem. For example, you can have it where you just simply ask where it is. So you can ask, if I give you this value x and L, tell me the location where it is if it exists. Otherwise, spit out -1, because that's on an index here. Notice that -1 doesn't exist right here. So it's a safe value for me to use, given no matter how big this array gets. That's one way I could go about this to define the search problem. But like I said, you can define this also on all sorts of other collections. You can even think of it as just a set, where the set is just an array that's being representing that given set, which is easy enough for us for our discussion. So if I use the word array here, you can easily switch this out for the word set for the definition of the search problem. Hopefully that's clear, everybody. But the big thing is that we're just going to make this presumption because it's easier enough for us to talk about at this level. So I thought, let's talk a little bit about how we could go about solving the search problem with like no assumptions about what is in these boxes. So I think it'd be a good place for us to start to talk about how could we solve the search problem if we're given an array L and a value x. How can I tell you that x is in L or not, as in it's in one of these boxes? Well, let's think of the most basic thing you might try doing. Now remember, when we develop an algorithm, which is an unambiguous, that means no matter how you read it to somebody, they're not going to misunderstand you. There's no two different interpretations of this that are going to lead you to two different outcomes or anything like that. It's going to be unambiguous. It's a step-by-step process where I give you input, in this case L and X, and it may even give me another parameter. Say, for example, you may want to know the array's length. Like, say if here I have 5 boxes, I may have that as well as one of the inputs too. So I have these two. I want to know so I give you inputs, it gives me output, and we want to know when the algorithm is correct. That means that the output is going to be what exactly should match for that given problem. Every one of the instances of this problem is an array with some value x. And keep in mind, there could be many, many, many different values for x, and there could be many, many values for L. So that means that it doesn't have to look just like this one. The array could, for example, have not just 5, it could have, say, 10,000 elements, each one with a value inside of one of its boxes. And the question is, okay, so how exactly can you search in such a construct, like this collection here? Well, you have to keep in mind, we can't just simply come up with something on the fly and be like, yeah, look, you just always pick box number 3 here. Just if you pick that one, you always will find it. See, that's not going to cut it probably to solve this problem, because if you think about it, suppose that value x was, say, in this box instead. You couldn't just simply just pick box 3 every single time, right? We might need to do something more systematic, right? We can't just simply just guess one of these and say, that's good enough, right? That's always going to give me the correct answer. So I have an interesting proposal. It's one of the most first things you might think of trying to do is as follows. Well, suppose I was looking for the number 7. Suppose that x is 7. So let me just draw a picture to help us kind of walk through this process. So I'm going to have 5 boxes. So I'm going to show you what this instance will look like. So I have my array. I'm going to call this one L because that's the name I gave it here. And it's going to have positions. So 0, 1, 2, 3, 4. Just like I have here. 0, 1, 2, 3, 4. And now there's contents in each one of these spots. Now, one thing I really want you to pay close attention to is that I need to have this developed in a way, because keep in mind, I'm making no presumptions what's in these boxes, right? It may as well be that I don't know what's in these boxes, in these spots in the given array. So I won't know until I check. So it wouldn't matter if I knew what position 2 had, or like box number 3 always was some value. If I could tell you that up front, it wouldn't make any difference because I might give you another instance where x is somewhere else. So I want you to kind of keep this in the back of your mind. This will be helpful for us to start thinking about how efficiently we could solve the search problem. So let's start off by just doing something I would consider pretty logical. So if I don't know where it is, and I have these indices starting here, perhaps it might be a wise idea to start right here, stay at position 0, check here, see if it matches x, and if it doesn't match x, then we go to the next box. And we try this again, and then try this again, then try this again. Well, let's see. Now, keep in mind, in our instance, we also have it where the value x is 7. And in the event that we need to know an n, in this case, that's the length of this array, we have 5. So let's kind of go through this. So at position 0, let's take a look. Okay, so we have a 3. So 3 is not 7, right? So we know that it does not equal 7. So far we've considered this one. Next, let's look at box 1 again. Let's remind ourselves what's in here. It's 5. That's not 7. Okay, so let's check box number 2. It has a 2 in it. Isn't that lovely? So it has a 2 in there. And now let's check box box 3. See, if you went with box 3, you'd get a 6. So in this case, a basic approach of picking at index 3 every time won't cut it, okay? So box 3 had a 6 in it. And then, of course, let's check the last one. Let's see. Look, it's a 7. Look, it's the 7. We found it. So in this case, we can answer yes, true, that it is that L contains 7. So it was just sitting in position 4. So in this case, the solution is true. And of course, the position it was at was not 7. That's the value that was at that position. It said it's 4. This tells me where it is. So in the event I'm returning back position, I'll tell you 4. If I just want to know if it's there or not, I could just tell you true. Either one of these will tell me the answer to this instance. Naturally, you can easily translate an answer like this into one that's like this. Because if I give you a number that is some non-negative integer, this will cut it. Because that will tell me that, yeah, it's there. So hopefully that is clear, everybody. So what I've just described to you, this process of us walking through each index for sweeping it from left to right, is something we would call a sequential search. I go through each element in my collection. And in particular, notice that this collection is linear. So we actually call this algorithm, the one I just described to you in our example, we call this linear search. So if you have linear search, you can, so here's the big catch, is I would like to know if this always works. Now it's very easy for me to be like, oh yeah, well we check all the boxes so we're all done, right? So we know that this is obvious. It's obvious that this is correct. Now that's what somebody that isn't thinking about this rigorously might tell you. They might tell you something along the lines of, oh well, we check all the boxes, so most certainly if there's nothing else, if I've compared all of them, then most certainly there's nothing here left, right? Well, that's one thing you can argue. Most certainly that is a true statement, is that if X exists in L, then most certainly checking all of them will cut it. But we want to be a bit more rigorous with this. We don't want to just say that. We want to say, why is it correct? So there's another way you can approach that same rationale to show that linear search is in fact correct. So I thought what I will do is I'm going to show using what we call an invariant. I'm going to show you how you can prove that this algorithm is actually correct, given this setup. So I'll first, after I identify this idea of an invariant, I will show you what linear search would look like if I wrote it out in pseudocode. Pseudocode, for those that are not initiated to this idea, is that very often people like to describe algorithms in a way that it's very easy to interpret and there's no ambiguity. So one standard way of doing this is trying to adapt the ideas that we have from computer programming. So for example, we would communicate in a programming-like syntax that isn't specifically tethered to any one language, though sometimes people will try to tether it a little bit to one language to help you understand some of the ideas, say if you're familiar with one language. But the whole point is that it's not really related to that. We want to describe the algorithm in a machine-independent way. Anyways, I want to talk about this idea of an invariant. So what I would like to do, so this is going to be something I really want you to pay attention to when I write out linear search. So an invariant, at least for our discussion, is to come up with so this is a property or relationship that is maintained during the execution of the algorithm. So there's specific kinds of invariants. The one that we're going to be using is what's called a loop invariant. So what this will mean is that every time I perform one major step or main iteration of what we call a loop, it maintains a special property, this invariant. And if we can ensure that this invariant always holds during each what we call iteration of that loop, if it happens each iteration, so before and after the iteration it maintains this property, then most certainly you'll maintain this property at the end. And naturally you just look at what happens at the end in relation to what the invariant tells you. So you're going to see this in a moment, okay? So let me describe linear search for you. So the big thing here I really want you to pay attention to is just how I describe this to you. So I'm just going to keep this rather simple for us. So we're going to talk about this algorithm. Usually when I describe an algorithm to you, usually it's a good idea, and this is just generally a good idea, is you describe what the algorithm is, you need to tell me what the input is and the output is. That's the framework that we use for problem solving in this setting. It's pretty common for computational problems. So suppose I give you L, N, and X. Just for sake of simplicity, reminder, N is the length of the array. Now you might ask, Dan, why would that matter? In some programming languages, you could just get the size or the length of an array, how many boxes we have, using library calls. Some programming languages, it's handy to actually have the number. So some languages, getting that is not as straightforward. So input So I'm going to give you the array L of size n. And we're going to be given a value x. So I have L and I have x. So as output, I'm going to tell you it's going to be outputting true. Is true if x is in L, false otherwise. So it's either going to give you a true or false. If x is in one of the boxes, like we had over here, then it returns true. The algorithm will return true. Otherwise, it returns false, meaning that it's not in any one of the boxes, any one of the positions of the array. So the first thing I'm going to do is I'm going to make a variable. This is going to be some sort of Boolean flag. Now, you might ask, Dan, what does that mean? I'm going to make this variable. I'm going to work under the presumption I have not found it yet, or that it just simply doesn't exist, because I simply don't know it does or not. This should remind you of something I said just a moment ago. So I'm going to presume I have a variable. I'm going to call this found. It's going to be set to false. This is because I want to just presume it's not there yet. If I encounter it, what I'm going to do is I'm going to flip this to being true. So if I can change this to true, that means that I've encountered x somewhere. And then when I'm done, I'm going to return if I found it or not. See, it's pretty logical, right? So now we're going to go through each one of the boxes, one after the other. We're going to start at index 0. So that's the first position, our leftmost box we had over there. So I'm going to have a counter variable. I'm just going to start it off at 0. So these are just assignments, by the way, just to be clear. So I'm assigning I to be the value 0. And it's going to check all of the positions. Notice that the last position is always one less than what n is. So now for each one of these, what did I do over there? What did I do over here? What did I do? I checked if in the box there was x, right? So that's what I'm going to do, just like we just described. So L sub I is equal to x. So I check if that is the case. If this is true, then I want to flip my found variable so that instead of being false, it's going to be true. So if I find it, then I'm going to update found to be true. So it's not false anymore. Now keep in mind, suppose that x occurs multiple spots in this array. It wouldn't make any difference. It will stay true. It never sets it back to false. Just please take note of that. There's nowhere in this loop now where it sets it to false again. So just keep that in mind. So the minute it finds one instance of x, keep in mind x may appear multiple times. Doesn't make any difference. Then after, we just return what found is. So whatever found is at the end of this process, that is going to be, what we're going to claim is that it's going to give us this as output, and it's going to match up in these cases. So it's going to be true if x is in L, meaning it's going to solve our search problem we had over here, our basic search problem.